Okay, we're still on lesson 9-7, and it says when x values in a set of data pairs have a common difference, you can analyze data numerically to find the best model. So here we have an example. So from -2 to 1, all I did was add 1. From -1 to 0, I just added 1. And from 1 to 0, I just added 1. So there's a common difference right there. And the same thing for the rest of them. They all have a common difference of 1. You can use a linear function to model data with y values that have a common difference. So here is an example of a linear function. I notice from -1 to 2, if I add 3, 2 to 5, add 3, 5 to 8, add 3. The difference is always going to be plus 3, so that means this has to be a linear function. You can use exponential functions to model data when the y values have a common ratio. Ratio is multiplying, so if I multiply 1/4 or 0.25 times 2, I get 1/2, or 0.5. 0.5 times 2, or 1/2 times 2, I get 1. And 1 times 2 gives me 2. So there's a common ratio, so that means it has to be an exponential function. The y values have a common difference of 3. It's a linear model. The y values have a common ratio of 2. It's an exponential model. For a quadratic function, the second difference are constant. So here we can see when the difference here between 1 and -1 is -2. From -1 to 1 is +2. From 1 to 7 is 6. And 7 to 17 is 10. So you wouldn't, from the first guess, it wouldn't seem like this is, we know it's not linear. So we'll look at the second difference. So from -2 to 2, common difference of 4. 2 to 4 is 4. And 6 to 10 is 4. So the second difference, so that means it has to be quadratic. So here we have, we're going to look at problem number 2. It says, which type of function best models the data? Use differences or ratios. So first, we want to verify that the x has a common ratio. And we see from -3 to 2, from -2 to 1, from -1 to 0, and from 0 to 1 is all a ratio, a common difference of 1. And so now let's look at the y value. So from 9 to 5 is -4, 5 to 1, -4, 1 to -3 is -4, and -3 to -7 is a -4. So that means this has to be a linear function. Again, we're going to check. So from 0 to 1 is 1, 1 to 2, I'm adding 1, 2 to 3, I'm adding 1, and from 3 to 4, I'm adding 1. So if I look from here, from 0 to -5, I get a -2.5. From -2.5 to -1, I get -7.5. -1 to -2.75, I get 1.25. And 2.25 to 4, I get 1.75. So the first round is not. Let's look at the second round. So 0.25 to 0.75 is 0.5. 0.75 to 1.25 is 0.5. And 1.25 to 0.17 to 1.75 is 0.5. So because the second difference are constant, it's going to say it's a quadratic. Let's look at guided number 2. It says which type of function which type of function best models the ordered pair. So I've written it here on my whiteboard, and I went ahead and written it in my put it in tally form. And as you can see, I have so -1.5, 0, 1, 1, 2, and then 2, 8, and 3, 4 are there. And so I'm going to look at my x values first. And so from here, I have a difference of, I'm adding 1. Oops. So from here to here, I added 1. From here to here, I added 1. And from here to here, I added 1. All right, so now let's look at the second one. So from 0.5 to 1, there's a difference of 0.5. So I added 0.5. From 1 to 2, I added 1. From 2 to 4, I added 2. And from 4 to 8, I added 4. Okay, let's look at the second row. So from 0.5 to 1, it's going to be adding 0.5. From 1 to 2, I'm adding 1. And from 2 to 4, I added 2. So it's not quadratic, it's not linear. So let's check to see if I'm multiplying by the same amount. I can do that by dividing. So if I do times 2, 1/2 times 1 gives me times 2, 1 times 2, 2 times 2 is 4, and 2 times 4 is 8. So that means that if I'm multiplying, that it's an exponential. So it's exponential model. Okay, so I hope this helps.